Welcome to part 2 in this series focusing on organic functional group reactions. This tutorial will also look at inorganic chemistry a bit because we're going to introduce the concept of oxidation, and reduction reactions. So let's get started. We'll begin with inorganic molecules. So when we see inorganic, we're going to say not carbon-based. But we will find as we study the organic functional groups, we will be using inorganic oxidizing and reducing agents at times. So it's important to understand this aspect of oxidation reduction chemistry too. So when we're focusing on inorganic molecules, we want to look at the charges. And linguistically, we also can call that oxidation numbers. So here are some guidelines for how we would assign oxidation numbers. And oxidation numbers, they're really helpful because they're a way to keep track of the electron flow. And oxidation and reduction reactions can be viewed as the flow of electrons. So really, at a very fundamental level, the formation of an ionic compound is an oxidation-reduction reaction because the electrons are transferred. The oxidation number is the charge on an atom in a compound that it would have if the electron pairs of each covalent bond belonged, right in quotes, to the more electronegative atom. So there's the rule. Let's practice applying it so it makes some sense. Anytime we have pure elements, right, they're neutral. So we would say their oxidation number is 0. So the oxidation numbers for iron or oxygen, right, are diatomic, are have no fear of ice-cold beer gang, 0. And then there's those good old fixed charged metals. Their oxidation number is always equal to their charge. The alkali earth, and aluminum, those are our buddies, right? And there's a few more fixed charges out there we could think of, right? For example, silver or zinc. Now, fluorine, since it's the most electronegative of the elements, it's always going to be -1. However, for the rest of the halogens, we have to look at the relative electronegativity. So for chlorine, bromine, and iodine, it depends on which element, right? Typically, it's going to be -1, especially if they're bonded to carbon. However, if we look at them bonded to other elements, right, with chlorine, for example, fluorine's more electronegative, so fluorine gets the -1, the chlorine would get the +1. So that would be, for example, like this compound here. However, if we have chlorine bonded with bromine, then we would write it this way because the chlorine would be more electronegative. Okay, oxygen, for our class, we can always assume oxygen is -2. It's oxide. However, be aware though that for peroxide, right, with the -2, O2 -2, right, peroxide does exist and does come into play sometimes, but this is not an emphasis in our course. And hydrogen's another easy one. We can always assume +1. If you go on in chemistry, you will learn that if hydrogen's combined with metals, it's a -1. But for our course, we can just focus on it in the +1 state. Alrighty, so now that we know how to assign oxidation numbers, we can look at the definition of oxidation and reduction that is most helpful when looking at inorganic reactions. And so there's a saying that can be helpful, and it's Leo says grrr. All right, so what's this about, right? So Leo, loss of electrons is oxidation. Right, so the Leo, right, loss of electrons is oxidation. There's our Leo. And then the Gur, you can see where this is going, right? Gain of electrons is reduction. Okay, so there's our Gur. So, and then the other expression that can be used is oil rig. And so one's not better than the other, just options for different people, right? So here, the O, oxidation, right, is loss. And for me, I just can't help, I gotta put of electrons. And then the R for rig, right, reduction, is gain of electrons. So most students find it helpful to write this little expression on the top of their page when they're working with oxidation and reduction reactions to help remind them. So if that's helpful to you, please take advantage of it. Alrighty. So now that we understand how to assign oxidation numbers, and we have the definition of oxidation and reduction, then we will, let's practice recognizing. So, right, so the first thing that I do when I'm going to practice is I write out Leo says Gur or oil rig. You know, reminding myself, right, that, let's see what colors, okay, right, so, right, oxidation is here, oops, right, and that's all about electron loss, right, electron loss. And reduction is all about electron gain. Okay, so by writing this at the top of the page, it's going to be a lot easier to answer these questions. So now let's actually get to the work. All right, so balance the following reaction. Oh, let's see. Oh, I didn't, okay. Balance the following reaction and assign the oxidation numbers. Alrighty, let's see here. So if we balance this, let's save iron for last because it's by itself. If we look here, we see we have 4 oxygens on the left, but we only have 2 here, so we'd have to put a 2 here, but then that's going to bump that up. We're not going to balance this one. We're just going to focus on assigning the oxidation numbers right now, because I should have done that before I started talking with you. All right, so let's just focus on the oxidation numbers, right? If we look at the iron here in this compound, what do we know? The oxide, oxygen's always -2. So that lets us know that our negative charge is -6. So the iron needs to be +3. All right. And then with the carbon monoxide, right, what do we know about oxide? Oxide always wants to be -2. So that tells us in this example, carbon is +2. Now let's look at our products. Here iron is shown in its pure state. Elements in their pure state are a 0. Here, carbon dioxide, right? Oxygen, we're always going to consider oxide. So there are 2 oxides for a net -4. So carbon is a +4. So when we're assigning oxidation numbers, the first thing we want to do is we look through our reactants and products and use the guidelines from the previous page. Now we can look here. So we can see that there's been a change in the oxidation number of the iron. It went from iron +3 to iron 0. So we would say, right, to get from plus to 0, the iron had to gain electrons. And therefore, right, the therefore symbol, this is a reduction reaction. At the same time that the iron is being reduced, we notice, right, the carbon, right, what's happening to the carbon? right? The carbon went from +2 to +4. So the carbon +2 to the carbon +4, how would that happen? It would have to gain negatively charged electrons. Oh, no. It would have to lose negatively charged electrons, right? It became more positive. So it's oxidized. All right. Okay. So basically we have the answers, right? So the carbon +2 is oxidized to carbon +4. To help you perhaps see, right, notice we could put the 2 electrons there, right? Now we have, on the left, we have a net +2, and on the right, we have a net +2. So these are the lost electrons. Simultaneously, right, the iron started as +3, right? So it would have to gain 3 electrons to become iron solid pure. So the carbon was oxidized and the iron was 3+ was reduced. Alrighty, so let's practice this one more time. And then we will do a complete half reaction. I kind of hinted to the half reactions, but let's do them formally. Alrighty, so step 1, look at the charges. Here we have copper with oxide, so a variable charge. So the oxide, of course, is the -2. And since since it's going to be -2 and -2, we're not going to worry about the oxide. We'll focus on that the oxide is helpful because it lets us know that the charge on the copper is +2. And then hydrogen, in its pure state, has 0 oxidation. And then just as the copper in its pure state as a solid is 0. And then because the oxide is remaining as -2, when we look at the hydrogens here, the hydrogens that are part of water, we can think of those as H+. And there will be 2 of them because of the chemical formula. Alrighty. So now if we look here, we say, okay, to get from copper +2 to copper 0, right, the copper would have to gain electrons. So this is our reduction. And the hydrogen is going from neutral to +1. So the hydrogen, to become +1, it has to lose electrons. So it is oxidized. Okay, so now let's formally do these half reactions. So it's very common in a redox to break it apart. So for the oxidation reaction, we have the hydrogen in its gaseous state. All right, and now it's going to lose electrons. So it becomes 2 hydrogen ions, and then this would be the 2 lost electrons. Notice that we are always going to maintain charge balance. If we're neutral on the left, we better be neutral on the right. 2, right? +2 and -2. Now the reduction reaction would be, here's the copper in the +2 state. So it is going to have to gain 2 electrons to become copper solid at 0. And then I think it's really important to notice, right, oxidation reactions have to occur together. So here we lost 2 electrons, and here we gained 2 electrons. And so not only does there have to be loss and gain, but it has to be the same number of electrons. We're not allowed to have any electrons floating around in space. Alrighty, so now that we have a good understanding of the oxidation and reduction of inorganic molecules, let's bring in organic molecules. We will use a slightly different criteria here for recognizing oxidation and reduction. So while the reactions are described the same way, we will evaluate them differently. So here the thing is, when we're looking at organic molecules, right, this is carbon-based chemistry. So we're going to so quite naturally, we're going to focus on the carbon. All right? So we're going to look at the number of carbon to oxygen and carbon to hydrogen bonds. Right? Carbon to oxygen and carbon to, hydrogen bonds. All right, so this is our criteria. So we don't worry about Leo says GR when we're looking at organic molecules. We look at the bonding to carbon. So oxidation, since we'll be focusing on biochemistry, we will just put an O in square brackets to indicate an oxidation reaction. And then this is a very important clue. We'll put hydrogen with square brackets to indicate reduction. So thinking about oxygen atoms with oxidation is very logical. But the new part for many people is thinking about hydrogen as reduction. Now notice this isn't a hydrogen ion. This is hydrogen. Okay, so oxidation is when we have a gain of carbon bonds to oxygen. So we'll have an increase in the C to O bonds. Vice versa, so if we think of oxygen as oxidation, so increasing that, or it could be the loss of carbon to hydrogen bonds. So we think about it two different ways. So then reduction will be the reverse. We'll have a decrease in the number of carbon to oxygen bonds, or an increase in the carbon to hydrogens. So you just want to start thinking about oxygen and hydrogen as opposites of each other. So one example here is a breathalyzer test. And so this will show us why we need to understand both organic and inorganic redox. So here we have, of course, ethanol. So the chemical in alcoholic beverages that gives us a buzz. And then here we have some chromic acid. And then here we have acetic acid. And we have an alternate form of chromium. So I don't want to try to give it away. Let's look. So the interesting thing about this is that this form of chromium is red, and this form of chromium is blue-green. So this is these inorganic oxidation and reductions are very helpful because they typically create a strong visual test to be aware of a reaction, where the ethanol and the acetic acid just look like clear liquids. They may smell a little different, but there's not much there. Okay, so let's focus on the change, right? So when we're looking at organic compounds, we're focusing on oxygen or hydrogen. So here we see that we have one carbon-oxygen bond. When we look at acetic acid, we see we have 3 carbon to hydrogen bonds. So, right, so here we have 1 carbon to oxygen, and here we have 3 carbon to oxygen. So ideally we would look at this, right, and recognize we've had an increase in the number of carbon to oxygen bonds. So this would be an oxidation. Now, to confirm that, so we can predict now that the chromium is reducing, but let's verify that, right? So if we look, the hydrogens would each be +2. So maybe we'll do this right. So the hydrogens are each +1, so that gives us a +2. And then the oxides would be 7 and then -2. So that would be -14. And then we have 2 chromiums, and we're not sure what the charge is. And we know it has to equal 0. So if we solve this algebraically, we will see that the chromium is +6. Now let's evaluate the charge over here, right? oxides are always, oxygen's always going to be oxide for our class, so that's -2, and we have 3 of them. So we have a net -6, and we have 2 chromiums. When we add those together with the charge from the oxygen, or the oxide, it has to add to 0. So algebraically, we should see that chromium then needs to be +3. Okay, so what happened to the chromium, right? Chromium went from +6 to +3. How would it do that, right? It would have to gain electrons. And gaining electrons is reduction. Alrighty, so here's a very practical example of how we can see inorganic oxidation and reduction combined with organic oxidation and reduction. So then the way the breathalyzer works is as the more alcohol, the more ethanol we have on our breath, the more blue-green will appear in the device. And there's ways to correlate the alcohol in the breath to the intensity of the blue-green color. Okay, so now let's go back to focusing just on organic molecules. So as we look at this next example, there's a couple things that come to mind. So a reducing agent, something that causes reduction, remember we think of that as adding hydrogen atoms. And then we need to focus on our reactant here, our organic molecule. So we look at the carbon chain, and I recommend never doing anything in condensed formula. Write it out. So if we write this out, we see we have a 5-carbon chain. And off this first carbon, CHO, you should be recognizing this as the aldehyde functional group. So now, if we're going to put this aldehyde functional group into a reducing environment, it's going to gain hydrogens, right, where we have the oxygen. So what would happen? So let's, oops, so that would be 1, right? So we'll get 1, right, so we go from 2 carbon to oxygen bonds to 1 carbon to oxygen bond. And then this hydrogen was already here, and so this hydrogen would represent the hydrogen from the reducing agent. So there's 2 main points about this question is start to think about the reduction process as the addition of hydrogen atoms like we've shown here, and then just a brief nomenclature little interruption. What would be the name of this organic molecule, right? This would be pentanal, Al for the aldehyde, and right, so this would be, and then this would be the alcohol. So and the name of this would be 1-pentanol. All right. Okay. So now let's practice recognizing oxidation reductions and organic reactions. So remember to think about oxidation as, oops, I showed you my notes instead of yours. Okay, so got a sneak preview there, right? So when we see oxidation reactions, we'll symbolize it with the square brackets and the O versus the H. Alrighty. So now the main thing is to look for change, right? So here we see alcohol or phenol groups becoming ketone groups. So here we had 2 carbon to oxygen bonds, and here we have 4 carbon to oxygen bonds. So we definitely had an increase. So we would describe this as an oxidation. On this second example, here we see the change. We're going from a double bond, an alkene, to a single bond, an alkane. wherever we have change, it can be very helpful to draw in the hydrogen atoms, especially now that we're aware of them in evaluating reduction. So here, carbon only wants 4 bonds. There are only 2 hydrogen atoms. Once the reaction is complete, though, we see that we have 4 hydrogen atoms in this region. So we went from 2 carbon to hydrogen bonds to 4 carbon to hydrogen bonds. Now obviously there's more carbon-hydrogen bonds in the molecule, but we're just looking for the change, so we can ignore. So we would put the symbol of H here, right, that this is a reduction. Whereas above, it was the oxidation. Okay, so let's have you practice this a little bit more. All right, so we're going to predict the products of the reactions below. And it's really important to remember, right, benzene rings are very stable, so they're not going to react. Okay, so we'll keep sliding this. There we go. All righty. So we focus on our functional group. So here's our aldehyde functional group. So here, if we're going to oxidize, right, we want to increase the number of carbon to oxygen bonds. So we're going to focus, this part's full, right, so we're going to add a O here. So we can oxidize aldehydes to carboxylic acids. Right, so we see, and then, so here we had 2 carbon to oxygen bonds, and now you see we have 3 carbon to oxygen bonds. All right, if we take the aldehydes, so aldehydes are interesting. They're a good place to study this because aldehydes can be oxidized to carboxylic acids, or they can be reduced to alcohols. So if we, remember, think of this as a H, not a hydrogen ion, but just simply a hydrogen atom. So we'll draw in the rest of the molecule. And then there is the carbon of interest. And this carbon of interest already has the 1 hydrogen present. And so now we're going to reduce this double bond to a single bond. And then here comes in, right, carbon wants 4 bonds. So the reduction adds that additional hydrogen to our carbon. So now we see that we only have one carbon to oxygen bond. So we would consider the alcohol the most reduced form, and the carboxylic acid as the most oxidized for this reaction pathway or series. Now we'll look a little more closely at this next reaction. So here we find our functional group, focusing on the carbon here. So alcohols, that's as low as we can go for having oxygen present. So if we want to oxidize, though, here, right, we only have 1 carbon to oxygen bond. So we can, right, oxygen likes to form up to 2 bonds. So we can oxidize this, right? So this would be 2 carbon to oxygen bonds. And now we have the ketone. All right. So a little bit of nomenclature here, just to have a chance to review. So this would be 2-butanol, and this would be 2-butanone. Okay. Up here, the names on this top, if you're curious about those as well, this is benzoic acid. Benzoic acid is a frequent food preservative. This is benzaldehyde. Benzaldehyde is often used as an almond flavoring. And then the alcohol would be benzyl alcohol. We'll just go with the common name. Okay, So there's some more practice on organic oxidation and reduction. So now we're going to bring in one last important concept, and that'll conclude this part of the series. So there's the language of oxidizing and reducing agents. So this is a very important concept that we need to be familiar with. And when you first hear about it, it can be counterintuitive, but there is an underlying logic if you just let it sit for a little bit, right? So an oxidizing agent, it's a reactant that gets reduced. That could seem like, did she make a mistake? But no, this is right. It's agent. To me, agent is the key word to help with understanding. An oxidizing agent, it helps other compounds oxidize. So you could think about it for me like when I started to make, it helps other compounds oxidize. All right. So for me, it makes sense. Like you think about agents, right? Like a movie star has an agent. The agent, we never see the agent in the movie, right? The agent helps the movie star get the jobs. Or the sports agent helps the athlete get the high contract, right, with lots of money. So an oxidizing agent helps other compounds oxidize, right? And so then that helps this second part make sense, right? So how does, right? So then this is the how, right? So how does an oxidizing agent help other compounds oxidize? Well, because by becoming reduced. And so if we focus back on our inorganic definition, right, we can think about it in terms of the electrons, right? So by gaining electrons that the other compound wants to lose. So there always has to be that exchange. I think, okay. Now let's look at reducing agents, right? So it's the same idea that with reducing agents, a reducing agent gets oxidized. So it's an agent of reduction. It helps, a reducing agent helps other compounds reduce, right? And so how does a reducing agent work, right? By becoming oxidized, right? So how, right? By being oxidized, because it's always a complement. Both reactions have to occur together. Alrighty, so let's look at this example here to practice working with the terms oxidizing and reducing agent. So if we look at our reaction here, right, the first thing we're going to do, this is an inorganic example, so we're going to assign our oxidation numbers. So zinc as a pure substance will be 0. And the chlorides, we can look here and see -1, so nothing's happening to the chloride. But the hydrogen is an ion, and then the zinc charge is here, and for a pure state, it's 0. All right? So we can look here and see what's happening to the zinc. The zinc went from 0 to +2, right? So it lost electrons. Lost electrons, Leo, oxidation. At the same time, right, what's happening to the hydrogen? It went from H+ to 0. So it gained electrons, therefore reduction. So there's our, so we found our redox reactions. Now we'll write the half reaction. So the oxidation half reaction is we start with the zinc metal. It's going to oxidize, and during the oxidation process, it loses 2 electrons. Simultaneously, we have the 2 hydrogen ions, and they are going to gain those 2 electrons to become hydrogen gas. So note that there's the charge balance within each half reaction, neutral, right, +2, -2, +2, -2. And then focusing again on this important concept of electrons lost have to equal electrons gained. Alrighty. So now for the new piece, these concepts of oxidizing agent and reducing agent. So the zinc is becoming oxidized. So because it's becoming oxidized, it allows the hydrogen to be reduced. So the zinc is a reducing agent. Simultaneously, the hydrogen ions are being reduced. Because they're being reduced, they're able to accept the electrons from the zinc. So the hydrogen ion is the oxidizing agent. Alrighty. Okay, so this was a big chapter of tutorial, and it's because oxidation and reduction is essential. This is how we get the energy from our food to keep us alive. So please take time now to work some homework problems, both focusing on inorganic and organic oxidation and reduction to reinforce your understanding.